When you jump out of a plane, you think you're just falling, right? But what's actually going on during that 1 minute of free fall? It's a full on high speed battle between two invisible forces. So let's break down the physics of what's really happening on that journey down. Okay, so picture this. You've just jumped. The wind is just roaring past you. For about 60 seconds, you're in what we call free fall. You're just plummeting towards the earth. But what does that term free fall really mean? Well, it all comes down to a few fundamental principles of physics. So here's where it gets kind of weird. You think falling is falling, right? But not everything falls the same way. Check this out. On the left, you've got this heavy steel ball, and you can see it's accelerating. It's picking up speed as it goes. But then look at the maple key on the right. It's just drifting down at a nice, steady speed. Same gravity is acting on both, so what gives? Why are the huge difference? Well, the answer is that there's an invisible battle happening. Yep, two forces are literally at war the entire time you're falling. You've got gravity, that relentless downward pull from the Earth, and then you have its opponent, air resistance. Think of it like friction, but with air, pushing right back up against you. You know, if we could get rid of air completely, say in a vacuum, then gravity would be the only thing acting on an object. And that right there is what scientists call free fall. It's kind of the perfect ideal state we use as a starting point. But of course, here on Earth, our skydiver has that pesky second force to deal with. All right, so let's dive into this invisible battle. We're going to follow the play-by-play of these forces, right from the moment you jump out of the plane to the second you hit top speed. Okay, so the very instant you leave that plane, your downward speed is pretty much zero, right? At that moment, gravity is in total command. It's pulling you down, and there's almost nothing pushing back. I mean, air resistance is there technically, but it's super tiny. So you start accelerating downwards and fast. But here's the thing. As you fall, you're picking up speed, and the faster you go, the harder that air pushes back up on you. So as your speed keeps climbing, that upward force of air resistance gets stronger and stronger, and it really starts to put up a good fight against gravity. So what makes this air resistance stronger? Well, it really boils down to two things. First, your speed, which we just talked about. The second is your cross-sectional area. Just think of it as your shape, or how much of your body is hitting the air as you fall. And this is the perfect way to picture it. Take a sheet of paper. If it's flat, it has a huge surface area, right? It catches a ton of air and just kind of flutters down slowly. But what happens if you crumple that same sheet of paper into a tight ball? The mass is exactly the same, so gravity is pulling on it just as hard. But now it has this tiny little area hitting the air, so it just plummets. That's cross-sectional area in action. So you keep going faster and faster until you reach a point where the upward push of air resistance gets so strong that it becomes exactly equal to the downward pull of gravity. The two forces are now perfectly balanced. The war, for now, has reached a stalemate. And this moment of perfect balance, that's what we call terminal speed, or terminal velocity. Because the forces are equal, the total force on you is now zero, and that means you stop accelerating. Now, don't get me wrong, you are still falling incredibly fast, but your speed isn't getting any faster. Okay, so we've been talking a lot about gravity as this downward pull. But what is it really? To get the whole picture of this fall, we kind of need to understand the force that kicks the whole thing off. I mean, think about it. The Earth doesn't actually have to touch you to pull you down. How does it do that? Well, it's because it's surrounded by what we call a gravitational field. It's this invisible zone of influence all around the planet that pulls on any object with mass that comes inside of it. Okay, so that leads to a pretty cool question. In school, you probably learned that gravity is 9.8 meters per second squared, or 9.8 newtons per kilogram. We use it like it's this constant number. But is it really the same no matter where you are on the planet? The answer is not at all. Check out this incredible map. This was made by the GRACE satellite mission, and it literally shows the little variations in Earth's gravity. The red spots are where gravity is a tiny bit stronger, and the blue areas are where it's a little bit weaker. So why the difference? What's going on? Well, the main reason is that the Earth isn't a perfect ball. It actually bulges out a little bit at the equator, kind of like a spinning basketball. And what that means is, if you're standing at one of the poles, you're actually about 21 kilometers closer to the center of the Earth than someone at the equator. And since you're closer, gravity's pull on you is just a little bit stronger. And this right here brings us to a super important point that trips a lot of people up: the difference between mass and weight. Your mass, that's the amount of stuff you're made of. It's measured in kilograms, and it never, ever changes, whether you're on Earth, the moon, or flying through space. Your weight, on the other hand, is the force of gravity pulling on your mass. So, because gravity changes depending on where you are, your weight changes right along with it. Okay, so let's get back to our skydiver. They're plummeting towards the ground at a very, very high terminal speed. How in the world do we get them down safely? Simple. You pull the ripcord. That parachute just blossoms open, and boom, you've just massively increased your cross-sectional area. What happens next? Instantly, that upward force of air resistance becomes way stronger than the downward pull of gravity. This slams on the brakes, and the skydiver slows down fast. And as they slow down, the air resistance gets weaker again, until it perfectly balances out with gravity one more time. But now, they're at a new terminal speed, one that's much, much slower. Slow enough for a safe landing. All right, let's wrap this up with one last kind of mind-bending idea. We've all seen it, right? Astronauts on the International Space Station, just floating around like they have no weight at all. But hold on a second. Think about it. The space station is only a few hundred kilometers up. That's really not that far. We know Earth's gravity is still super strong up there, so are they truly weightless? And the answer is nope, not at all. In fact, they still have almost all of their weight. The reason they look like they're floating is because they are in a constant state of free fall. The station, the astronauts, every single thing inside it is continuously falling towards the Earth. The only reason they don't crash is because they're also moving sideways so incredibly fast that they constantly miss the planet. That floating sensation, that's what free fall actually feels like. So let's wrap this all up. What did we learn? First, that falling is really a battle between gravity pulling down and air resistance pushing up. We saw that terminal speed is what happens when those two forces finally call a truce. We learned that your weight can change depending on where you are, but your mass, that's with you forever. We figured out that a parachute is basically a giant air brake that wins the battle for you. And maybe the coolest part, that weightlessness we see in space, it's not weightlessness at all. It's just a continuous, never-ending free fall. Which leaves us with one last thing to think about. Imagine you're in an elevator, and the cable snaps. For a few terrifying seconds, you and the elevator car are in free fall together. So, based on everything we've just talked about, what would you feel in that moment? Would you feel weightless?